So this is another concept bite, this time on the quenching of excited states. If I consider an excited state and the fate of that excited state, I have various possible routes of it being lost. First off, I have emission, fluorescence, if it's from a singlet state. I also have the possibility of internal conversion and the singlet to triplet into system crossing. If I introduce a new term, quenching, I'm going to reduce the quantum yield of my system. Quenching can occur from both the singlet and the triplet state. However, it is only quenching from the singlet state which will affect the fluorescence quantum yield. There are various methods of quenching, principally static and dynamic. Static quenching is where a complex is formed, whereas dynamic quenching is caused by collisions of my fluorophore and my quenching molecule. In dynamic quenching, there are various ways that the energy can be lost, either by internal conversion or I can form an excited state on my quenching molecule. I can also undergo chemical reactions. There is also quenching at a distance, which covers Forster and Dexter energy transfer and electron transfer, but I'm not going to discuss those in this video. Static quenching is where we form a complex between our fluorophore and our quenching molecule. In the unbound state, the fluorophore is free to emit light as fluorescence. However, in the complex, the fluorescence is completely quenched. In this case, the lifetime would be 0. There is absolutely no emission from the excited state. So I go from an unquenched lifetime to a completely quenched lifetime. This is a simple equilibrium process, and I can have an equilibrium constant for it based on the equilibrium concentrations of the complex and the unbound states. If I think what's going on in terms of energy levels, in my free fluorophore, I can have emission from the excited singlet state. However, when the complex forms, all energy is going to be lost as internal conversion. If I think about this in terms of what goes on from a graphical point of view, I can plot a simple graph of I naught over I. The quenched intensity is I, the unquenched intensity is I naught, and I can plot that against the concentration of the quencher. This gives me a straight line graph with gradient Ks, my equilibrium constant for the static quenching. As I increase the temperature, the amount of quenching is reduced, the emission increases, because the weak bonds in the complex formation are going to be broken and my equilibrium is going to be driven towards the left. Dynamic quenching occurs by collisions in my molecules. I go from my singlet excited state to my ground state, and it doesn't matter the fate of that excited state, all that matters is that it is quenched. In this case, I naught over I is equal to tau naught over tau. The lifetime is quenched at exactly the same rate as the intensity or the quantum yield. I can plot a straight line graph again. In this case, it's again linear in terms of a plot of I naught over I against the concentration of the quencher, but the gradient of this line is made up of two terms, kq, the rate of quenching, and tau naught, the lifetime of the unquenched excited state. If all collisions result in quenching, then my rate of diffusion control is the same as my rate of quenching, and I can easily calculate the rate of diffusion control using this equation at the bottom, 8RT over 3 eta, where eta is the viscosity of the solvent. Remember in this case that there is usually a conversion of units to be made if we're going between a rate constant, which uses per mole per litre, and a viscosity which uses meters rather than litres. In the case of diffusion controlled quenching, as I increase the temperature, I'm going to increase the amount of quenching that I observe, because I can see from this diffusion controlled rate there is a temperature term there. I have more collisions as I increase the temperature. This also has an effect on the lifetime. Here I've got a blue unquenched line and a pink quenched line, and the corresponding equations for lifetime are given in the boxes. The unquenched lifetime has one fewer term than the quenched lifetime, and so the quenched lifetime is going to be shorter. It does still follow first order decays though. So just to recap, static quenching is formed when I have a complex. There is no observable fluorescence from a statically quenched system, so I have a mixture of unquenched and completely quenched molecules. So I see no effect on the lifetime in this case. The lifetime of unquenched molecules in this case. If I increase the temperature, I'm going to decrease the amount of quenching I see, increase the amount of emission, because I'm driving the equilibrium to the unbound state. In dynamic quenching, the collisions are causing the quenching. If all collisions result in quenching, the rate of diffusion is the rate of quenching. If they don't, it's just a proportion of this. If I increase the temperature for dynamic quenching, I'm going to increase the amount of quenching because I'm going to increase the number of collisions. And in the case of dynamic quenching, lifetimes and intensities are reduced at the same proportion. Sometimes I can get a combination of static and dynamic quenching. In this case, if I'm given lifetime data, it's easy to separate the two out. Hope this helps. Just let me know if you've got any questions.